So welcome to this new video related to the Neos-II processor, which is the soft core of Intel. The Neos-II processor is a RISC processor that is quite similar to the microblaze that we've seen so far. It's a 32-bit processor, and it has been introduced in 2000 in its first version, then in 2004 for the second version. Today, this processor is one of the most popular soft core in the Fpga world. It's a processor with 32 general-purpose registers, 3 instructions format, 32-bit instructions, and 32-bit data path. Just like the microblaze, it also has a separate instruction and data cache with configurable sizes. It also has tightly coupled memory options and is able to perform branch prediction very efficiently. 32 prioritized interrupts are also available in this processor, and designers may use on-chip hardware to accelerate some of the operations like multiply, shift, and rotate. It's also possible to add some custom instructions to accelerate processing. There's also a JTAG-based hardware debug unit used to debug a program at runtime. So the Neos-II processor comes with 3 different flavors. A standard version here is available with certain features like 5 stages of pipeline, a possible use of the hardware multiplier, which is available in the Fpga side. And these operations are performed in 3 cycles. In this version, the branch prediction is static and the instruction cache is configurable. In the standard version, there's no data cache. So if you take a look at the table, you see that this current version requires 1,200 logic elements, which is the standard size of the processor. If you want to reduce the size of the processor, you can opt for another version of it, which is called the economy version. And it's depicted in the 3rd column here. In this new version, there's no pipeline, there's no possibility to perform hardware multiplications or barrel shifter in hardware, and everything is emulated in software, which means that the operation is going to take a long time. Furthermore, there's no branch prediction, there's no instruction or data cache in this type of processor, which is very, very simple. One advantage of this economy processor is the size, since it's only 600 logic elements compared to the 1,200 for the standard processor. On the contrary, if you want to have fast and very efficient and performing processor, you can choose the fast version of the Neos-II processor. In this case, you would have a 6 stages pipeline processor, which is able to perform a hardware multiplication in only 1 cycle. Here, the branch prediction is dynamic. Moreover, the instruction and data caches are configurable for much flexibility. Nevertheless, in this new processor, the logic resources are much higher, since it requires 1,800 logic elements without a memory management unit, or MMU. So if you want to add this memory management unit, for example, if you want to implement an operating system on top of the processor, then it will require 3,200 logic elements. So the 3 versions of the processor come up with 256 custom instructions that make it possible to access hardware accelerators very efficiently. And this we will describe later, the different process. Here is the architecture of the Neos-II processor. The fixed elements are the program controller and address generation block, here in brown. Then you may find a bunch of general purpose registers, as well as status and control registers. This is provided by the vendor and cannot be changed. There are also configurable modules within the processor that are the arithmetic and logic unit in gray, the exception controller, and the interrupt controller. Furthermore, an additional instruction and data cache memory here can be implemented depending on the flavor of the processor you want to deal with. There are also debug options implemented in the hardware breakpoints module here that can be used to stop the execution of a program. It gives access to the contents of the different registers, which can be very helpful when you want to debug a program. You can also have instruction and data trace that is used to have access to the memory contents when you want to debug a program as well. Finally, you can add a custom instruction logic block, which is very close to the arithmetic and logic unit, and that can change its functionality to take into account the new instructions that you can use in your program. Well, we get back to this situation a little bit later. There are also tightly coupled instruction and data memory to provide very efficient access to both instructions and data. Another option is to implement what we call the MMU, which stands for Memory Management Unit here. The MMU is a hardware component that is mainly used to deal with virtual addresses and that translates virtual addresses into physical ones. The MMU is mainly used by an operating system, which manages the virtual addresses. You can also decide to implement an MPU instead. In this case, it's more simple, and it's only used to protect some memory spaces when you want to use a particular application. So if you take a look at the Memory Management Unit, or MMU, I've just said that this MMU is mainly used by an operating system to ensure protection and isolation of different applications running on top of the processor. This provides memory protection and virtualization. It divides the memory space into 4 kilobyte virtual pages that may be accessible by the applications running on the operating system, and this block maps virtual addresses to physical ones. It also provides a specific access permission to these pages. In fact, there are 3 types of permission. A page may be used in read, write, or execution mode. It ensures that a particular application cannot disturb the others in their functioning. The Memory Management Unit is managed by an operating system and not directly supported with the Intel tools or the other functions that you can find in the library. In fact, you need a given operating system that manages virtualization to efficiently handle this MMU. So most of operating systems like Linux or FreeRTOS are examples of operating systems that can manage this MMU. The Neos2 processor also comes with the configurable software debug unit, which is based on JTAG, and makes it possible to download pieces of code from a PC, for example, to the processor. This is completely managed by this block. It also enables software breakpoints or even hardware breakpoints if you want to debug a program during its execution. Once again, this JTAG debug configuration module comes at different levels depending on the information that you want to get during the execution. For example, a basic JTAG target connection requires 300 to 400 logic elements. If you want to have a very efficient debug, then it will require more than 3,000 logic elements to get access to software breakpoints, instruction trace, data trace, on-chip and off-chip memory traces. Now we're going to see how we can scale performance, that is to say, how we can play with the Neos2 processor to obtain even better, higher performances. The first way to obtain better performance is to build a full multiprocessor system within an FPGA. Since the Neos2 processor is a soft core, it is completely feasible to implement several instances of the core and add the different cores inside the Fpga. We can also couple this multiprocessor system implemented inside the Fpga to external CPUs or even DSPs. Another way to obtain performance is to use custom instructions. In this case, we accelerate individual CPU by adding some application-specific instructions. In fact, you will modify the ISA of the processor to add some functionality inside your arithmetic and logic unit. Finally, the third way to obtain better performance is to use hardware accelerators that are implemented in the Fpga reconfigurable area. These accelerators implement some basic or complex computation like filters, complex DSP, FFTs, or whatever, and is tightly coupled to the CPU. In the first solution, that consists in building some multiprocessor system, one of the most important issues to deal with is how to make processors communicate with each other. In this case, one has to provide some mechanism to ensure that the communication and the execution of the program are going to be handled efficiently. Intel, for example, provides objects called mailboxes that enable interprocessor communication. This can be seen as global buffers that are accessible from and to several CPUs. In the example here on the left, you'll see that CPU 0 is going to write data to a buffer A. Data that are going to be stored here can be read by CPU 1. The same thing is handled by buffer B that can be used to write from CPU 1 to CPU 0. So these buffers consist of shared memory in which different CPUs can read and write data. Another problem related to the multiple CPU system is that they often share the same hardware or software resources. In this case, one has to provide some basic mechanisms to protect the different resources and to avoid CPUs to have access to the same resource at the same time, which leads to a conflict in this case. Again, one has to propose solutions to share these resources. For example, we can use the concept of hardware mutex, which is well known in the software domain and that is closely related to the lock principle. For example, if the CPU wants to have access to a resource, it can get the mutex that is going to be locked for this CPU. If another CPU wants to access the same resource, then there's going to be a problem because the mutex is already taken. So in this basic example, CPU 1 wants to have access to the UART, for example. It takes the mutex. If CPU 0 wants to have access to the UART at the same time, it's going to ask for the mutex, which is not available. In this case, CPU 0 will have to wait for CPU 1 to release the hardware mutex to have access to the resource. Note that all functions implementing these mechanisms are provided by the vendor, even if it's in hardware. The other way to obtain better performance is to use custom instructions. That is to say that we're going to modify the functionality of the arithmetic and logical unit. This unit has two inputs, A and B, and one output, and performs basic operations on data. Actually, it can be seen as the most important part of the processor. Custom logic is added to the arithmetic and logic unit to perform additional operations. This is, for example, ideal for math and logical operations like floating point calculation, bit manipulation, etc. The main idea behind that is that hardware is much faster than software, and if you want to perform some basic operation, then you can have a dedicated hardware unit to perform this operation very efficiently. So if you perform a specific operation very often, this is very interesting to implement this operation in hardware. For example, here you see that a custom instruction makes it possible to go 27 times faster than a program running without any specific custom instruction. This is made possible because the custom logic hardware can be implemented in the reconfigurable part of the Fpga. The best way to improve processor's performance is to use hardware accelerators. An accelerator can be seen as a coprocessor that helps the CPU in its task to perform some specific computation. Here's an example with a CRC module that is going to help the processor in performing some basic tasks on data. In this case, the CPU is going to start and stop the coprocessor here. The coprocessor will fetch data and store the results somewhere in memory. This is very efficient because the CPU can run an application code concurrently, meaning that it can do something else while the coprocessor is working at the same time. The coprocessor, or IP, is connected to this CPU through a bus that is managed by an arbiter, and all modules communicate through this bus. This solution is very efficient, and we see that using a coprocessor can accelerate processing with a factor of more than 500, which is a lot compared to custom instructions, for example. Using other accelerators in an Fpga is something that is very common today, and is actually one of the most important advantages of current Fpgas. For example, there are a lot of vendors in cloud computing that make use of Fpgas to accelerate some processing for artificial intelligence that requires a huge amount of computing resources. Fpgas are very well suited for this kind of applications since they can execute a lot of functions in parallel without consuming too much power. Now we're going to take a look at the interconnections between the different modules of the Neos-II system. All modules are connected through the Avalon standard, which is an interface specification for on-chip components. It defines the types of transactions on the medium. Right now, there are 3 different types of interfaces. The first one is what we call the Avalon ST, which is a streaming interface that describes the way the modules can communicate through FIFOs to exchange data. The second interface is the memory mapped interface, in which all modules are mapped in the memory at a given address. The third one is what we call the Avalon Tri-State, which describes the connection to other off-chip modules. The Avalon is a master-slave system. A master initiates transactions by sending data or sending a request, and the slave responds to the master request. This is how it works. This figure summarizes all the Avalon interfaces that you can deal with. The blue rectangle here corresponds to the board in which the Fpga is going to be implemented. The Fpga itself corresponds to the white rectangle. In the Fpga, we see different blocks, the Neos2 processor, and the different peripherals that are connected to the processor through the Avalon bus. The modules that are connected to this bus have an associated address that makes it possible to communicate with each other. Another very important interface is the Avalon clock interface. Here you see the PLL block, which is connected to a reference clock coming from the outside of this Fpga. This clock is usually generated by an oscillator that provides a rectangular signal with a given clock frequency. The PLL block outputs 2 signals, C1 and C2, to drive all internal components. That's why this PLL is very important. Note that C1 and C2 may be different, meaning that the frequency, the offset of these signals, may be different. If you take a look at the different components here, you see that they are either connected to C1 or C2. For example, the Neos-II is driven by C1, as well as the timer and the SRAM controller or the flash controllers. Other peripherals are driven by C2. This is the case of the DDR3 controller and the scatter-gather DMA. Another interesting thing is that components can also communicate with each other through point-to-point connections with the Avalon ST interface. This is the case here of the Ethernet controller, for example, which is connected to the scatter-gather DMA through FIFO buffers. So here you see that the Ethernet controller is connected through a FIFO from its source port to, and there's a sync port on the other side to receive data. This type of interface is unidirectional. Another interface is the Tri-State connection. In this figure, you can see TCM, that stands for Avalon Tri-State Master, and TCS, that stands for Avalon Tri-State Slave. You can see here that a master is always connected to a slave. This is the case here for the SRAM controller and the Tri-State Conduit pin sharer. That is a block that is used to share pins between different modules. Another interface is the Avalon Conduit. This interface is used to connect a specific component within an Fpga with a component that is located outside the Fpga. It's a bidirectional link. Finally, this figure summarizes all the interfaces that are available in the Fpga, and we're going to play with these interfaces during the lab. So make sure you understand the very principle of each interface. Now we're going to study the Avalon interfaces in detail. Each interface has its own signals that comes with three types: the address signals, data signals, and control signals. All operations that are performed on the bus are synchronous. Usually all signals are active high, unless it's followed by /n, which means that they are active low. For example, read _n means that this signal is going to be active at 0. We give here the example of the Avalon memory slave port. The different signals of the Avalon memory mapped slave interface are depicted here. A clock signal, coded into 1 bit, is used to ensure synchronization. The chip select signal is also very important. If the signal is not active, the slave ignores all other signals. It's available as an input of the slave. The address signal 1 up to 32 bits corresponds to the offset in the slave memory space. The read signal indicates a read request from the master. It's only coded into 1 bit and is also available as an input. If present, read data is also required. In this case, this new signal provides data at a given address that was previously indicated by the address signal, and the signal is up to 1024 bits. The write signal indicates a transfer. If present, the write data signal is also required and consists in writing data at a given address. Write data is also available as an input. Byte Enable is another signal that selects bytes to be transferred. For example, if Byte Enable is 1111, it means that it's possible to write the full 32 bits. A value of 0011 only writes the lower 2 bytes. A combination with 0001 only writes the least significant byte. Write Byte Enable, this one, is a combination of the Byte Enable and write and is available as an input. Finally, the begin transfer signal is automatically implemented and is equal to 1 during the first cycle of a data transfer. These signals constitute the fundamental signals for the Avalon memory map slave interface. The master's signals list here is nearly the same as the slave interface. The signals are often in the opposite direction. That is to say, when it's an input in a slave, this signal becomes an output when it comes to the master signal interface. In addition, there are two signals which are denoted flush and RRQ number. And these signals are used for retransfers with latency. A master can clear any pending latent retransfers by asserting this specific flush signal. The IRQ number is an interrupt priority on each slave port. A bunch of signals is not included in the master interface. These signals are output enable, chip select, write byte enable, begin transfer, begin burst transfer, read ready for data, and data available. The 16 general purpose I/O peripheral shown in the following figure only responds to write request. This component includes only the slave signals required for write transfers. Each signal is in an Avalon memory map slave corresponds to exactly one Avalon memory map signal role. An Avalon memory map interface can use only one instance of each signal row. The figure here shows an example of the fundamental read transfer. In the Avalon Retransfer, the bus transfer starts on the rising clock edge, as you can see here. For the transfer to complete in a single bus cycle, the target peripheral must immediately and asynchronously output the contents of the address location to the Avalon Bus module. On the first rising edge of clock, the Avalon Bus passes the address, byte enable N and read N signals to the target peripheral. The Avalon Bus module decodes the address internally, then generates a chip select and drives the combinatorial chip select signal to the slave port. Here. Once chip select is asserted, the slave port drives out its read data as soon as it's available. Finally, the Avalon Bus module captures the read data on the next rising edge of the clock. This fundamental retransfer with zero wait states is appropriate only for truly asynchronous peripherals. The target peripheral must present data to the Avalon Bus immediately when the peripheral is selected and or if the address changes. For the transfer to work properly, read data's output must be valid and stable by the next rising clock edge. The example 2 shows a slave retransfer with one wait state. The Avalon Bus module presents address, byte enable, read N, chip select during the first bus cycle. Because of the wait state, the peripheral does not have to present read data within the first bus cycle. The first bus cycle is the first and only wait state. The slave port may capture address and control signals at any time. During the second bus cycle, here, the target peripheral presents its read data, to the Avalon Bus. And on third and final rising clock edge, the Avalon Bus module captures the read data from the slave port and completes the transfer. The example 4 here shows a slave retransfer with peripheral controlled wait states. The peripheral controlled wait state mode uses the wait request signal, which is an output from the slave port. After read N is asserted to the slave port must return wait request within the first bus cycle if it wishes to extend the retransfer. When asserted, wait request stalls the Avalon Bus module and prevents it from capturing read data. The Avalon Bus module will capture read data on the next rising edge of the clock after wait request is deasserted. The Avalon Bus module doesn't have a timeout feature to limit how long the slave port can stall. When the Avalon Bus module is stalled, somewhere in the system module, there's a master peripheral that is stalled as well, waiting for the requested data to come back from the address slave peripheral. A slave port could permanently hang the master port. This could be very dangerous. Therefore, the peripheral designer must ensure that a slave peripheral does not assert wait request indefinitely. The last example, example 6, here shows the slave write transfer. In this configuration, there are 0 wait states and no setup time or a hold time wait states. The Avalon Bus module presents address, write data, byte enable, write n, and then asserts chip select. The slave port captures the address data in control on the next rising clock edge, and the write transfer terminates immediately. The entire transfer takes only 1 bus cycle. The slave peripheral may then take additional clock cycle to actually process the write data after the transfer terminates. If the peripheral cannot sustain consecutive write transfers on every bus cycle, then additional design considerations are required to generate wait states. Well, that's all for the bus transfers. I hope you enjoyed this video, and see you next time.